Antonu, hey. অ্যাডমিট করো না, ওটা ইয়েস করো, ঢুকতে চাইছি। অ্যাডমিট অল করে দাও নিচে। ভিডিওটা অফ করো। হ্যাঁ মিউট করো, মিউট করো। কনভার্টের জন্য হচ্ছে চেয়ারের এই চেয়ারের কনভার্টারটা লাগাতে
Keep quiet, please. Please take your seats. Volunteers, please take your seats. A very good morning to one and all present here. Respected Chief Guest Professor Dr. Subal Gaur, Honorable Professor Dr. Isha Mishra, online. Chair IEEE, Kolkata Section, Honorable Principal Sir, Professor Dr. Sanjay S. Power, Vice Principal Sir Professor Dr. K. Hussain, HOD EC Dr. Lorendranath Pathak, and my dear colleagues. It gives me immense pleasure to welcome all to the 5-day workshop on metamaterials and metamaterial assisted backrometric devices. First of all, I would like to request our Chief Guest Professor Dr. Subal Gaur, Principal Sir Professor Dr. Sanjay S. Power, Vice Principal Sir Professor Dr. K. Hussain, and HOD EC Professor Dr. Lorendranath Pathak, and convener of the workshop Professor Dr. Sharif Pal, and one of our honorable speaker, Professor Dr. Tapas Mondal, to take their seats on the dais. Sir, please. workshop is a joint venture of Department of Electronics and Communications, Dr. Vishnu Engineering College, Durgapur, and thinkers of Vacuum Electron Device Group, India, and technically co-sponsored by IEEE Kolkata section. Honestly speaking, this workshop is a brainchild of Professor Dr. Raghunath Basu, well known as B.N. Basu, ex-professor of IIT DHE. Recently, Professor B.N. Basu has been awarded highly prestigious IEEE IBEC GR Pius Award 2023. He is the first Indian to receive the award. It's a recognition of India's strength in vacuum electron devices that Professor Basu has been instrumental in carrying out theoretical research and guiding several generations of students and scientists over 4 decades. Now, we have our traditional lamp lighting ceremony. I would like to request our honorable guest to enter the lamp. Sir, please.
আচ্ছা ইয়ে কিছু দেখতে পাচ্ছেন বলছি অডিয়েন্সটা অনলাইন কিছু দেখতে পাচ্ছেন
এই স্ক্রিন থেকে ইয়ে করে
ঠিক আছে আমি দেখছি অনলাইন
এটার লিঙ্কটা চলছে
হ্যাঁ হ্যাঁ স্যার
ইউটিউবের লিঙ্কটা আমাকে
লিঙ্ক পাঠাচ্ছি হ্যাঁ স্যার
Thank you, sir. Please be on the dais. Now, I would request our principal sir to felicitate our chief guest, Dr. Shubhal Kaur, with Uttoriyo. And bouquet. Thank you, sir. Now I would request our Vice Principal sir to present our chief guest, the visionaries, the booklet published by ABP Anando to celebrate their 100 years of journey, which contains the visionaries of Isidoi group of colleges. Please, sir. Thank you, sir. Now I will request our HOD sir, Dr. Emil Patel, to present the BCIC memento to our chief guest. Thank you, sir. Now I would request our principal sir to deliver his welcome address. Sir, please.
Good morning, all of you. It's a pleasure to have a legendary here in the field of microwave, Mr. Subhankar, with his experience and knowledge. It's really an honor or pleasure to us as to be a inaugural session of this workshop, and look forward again guiding into these areas and inspire our faculty members and students into this world of microwave and metamaterials. Faculties, these are some kind of special subjects, special areas where rather than external inspiration and internal inspirations are required to carry out the work of this kind of areas and so on. Though I am not directly more into these areas from the research and other maybe interest point of view, but indirectly I have been involved into these activities by some or other means because of my area of interest of 5G and optical network. These are the areas where a lot of understanding, visualization, practices, analysis are needed. And believe me again, as we have been speaking in morning also, this area of RF engineering is presently the highest paid jobs as far as I remember, which has been, if you check the ranking into the specifically US market or European market, RF engineering is the highest paid job that are available. The reason is a lot of work is required, a lot of dedication, a lot of understanding is required, and very less people are involved into this activity. That is one of the reasons. Though there is a huge rush going into the area of software, etc. and so on, but on all these things, built specifically from the telecom side is of course the hardware and antennas and microwaves. To some extent, during my MTech period, I had carried some of my work into these areas of microwave. Two subjects that I had learned was antennas and microwave devices and circuits. Where I understand again what is the dedication, knowledge and information required specifically from understanding these subjects like this area. As far as the topic of the today, the metamaterials and applications, as there is a huge areas of applications, what I am more concerned is rather than interest is again from the 5G and 6G point of view, where the RIS reconfigurable intelligent materials are used in case of a future band that is being considered as a new radios, which is FR1, FR2, and FR3, or when we consider FR2, it's approximately I think 25 point some gigahertz to 50 gigahertz, and next band is of course in the range of 90 gigahertz to above and so on. Technically, the things behave very differently in this band, and sometimes it becomes difficult to predict these areas also. And to know all these things, of course, it requires basic knowledge of this area, microwaves, and how the frequency behaves in that area. That's where the sir expertise comes into picture, and we would like to listen more into this area from the sir. In addition to that, what I would like to have a help from the sir is, as I have been discussing, a lot of research proposals may come into picture, and our research organizations such as BST is there, DRDO is there, ISROs are there. A lot of expertise and projects are expected. Let us have some kind of input guidance. I think sir yesterday morning I was saying tomorrow sir will be free. We can have a formal discussion with the faculty members in these areas that would lead us into writing some kind of a proposal to these areas where help from the sir will be helpful. We look forward towards helping us sir in these areas and creating an interest among the faculties and students with the futuristic vision in this area also. Thank you.
Thank you so much, sir. Now I will request E.T. Saha Mishra, Chair Arithmetic Kolkata section to address us. She is online today, so I request everyone to log in the provided link for the workshop.
Domain of wireless communication and network. I am the professor and former HOD of Electronics and Telecommunication Engineering Department, and I have the author of few of the books on the domain of wireless communication. One of the textbook, wireless communication, 3G networks and beyond, is getting importance everywhere within India. This is in brief working and several patents in the domain of wireless communication and networks are there. I have developed the broadband wireless communication lab in the Department of Electronics and Telecommunication Engineering. I'm sorry, the computer is not properly working, that's why I had to stop this thing. But I would like to say something regarding the organizer. I didn't get any detail of the speaker, today's speaker. Only day before yesterday I got the invitation letter. So I think this organization and little bit hampered because earlier whatever the event organized by the Physical Engineering College, I was personally present there and I teach them how to organize. But every time I see they are little bit unorganized and do not follow the time management. So it is very, very essential whenever you are the part of the ICT community, apart from the technical session and events, you have to organize the good timing management and other things because all the valued speaker and other disciplines and organizer waiting for a long. I myself waiting from the time 10:50 and I could not join your network. So that is the thing. In future, my advice would be that you have to have more organized and time management. So I have seen from this board that there are several distinguished speakers are here. I could see my professor from radio physics and electronics, Professor Shubhal Kaur. Sir, by respect to you, I am Itisha Bistro. Do you remember me? I don't know. Yes, but I could see you here. Professor P.S. Basu, L.M. Joshi, Professor Claudio, Professor Shivan Kak. So my regards and respect for coming here. I think the 5 days workshop on the very urgent topic of metamaterial and metamaterial assisted vacuum electron device would be very, very successful and all the participants will be benefited out of this workshop. I wish the grand success of this thing. I am not a person of the metamaterial, but what I understand only that metamaterials are structured material with some wavelength features that can be engineered to have some unique properties not found in the nature, such as negative refractive index, that was Doppler effect, etc. And it was first investigated by Mr. Lagori in the year of 1967. Now it is a big hot topic, especially the meta surface at present receiving much attention, especially in the domain of optics. So this is a very timely event of providing good knowledge on this subject so that the participant would get would be benefited in the day-to-day engagement of this research and development happen. That is the motto of the IEEE, the technology evolution for the use of the mankind. So I thank you all, my respect to all the panel speakers and thanks to the organizers. Thank you.
Thank you, ma'am. Your suggestions are cordially accepted and that will be taken care of in the next event, I assure. Now I would request Professor Dr. P.N. Basu to deliver his pragmatic experiences and share his experiences with us. So please.
Good morning, everybody. Am I audible? Yes. Am I audible?
Yes.
Yes, you are audible. Thank you very much, Professor Khan. Very much thankful to the organizer. Particularly Professor Sarifa for meticulously making the program. He has been working very hard for all these days. I congratulate him and his team, dedicated team. Many congratulations to Professor. So I have been asked to say a few words well, my introductory remark is like this. Metamaterial belongs to the category of artificial materials. Enkeheta and Yolandi in the book edited by them wrote, Jagadish Chandra Bose conducted the first microwave experiment on twisted structures, geometries that were essential, artificial, guided rings like today's. Well, he was referring to the Yeshivo's paper in Professor Muslims of World Society in 1898. The particular paper is entitled as On the Rotation of Denocularization of Electric Wave by a Twisted Structure. It is in Philosophy Royal Society, published in 1898. Okay. I am happy to inform you that in parallel with global efforts in improving the performance of microwave lenses, phase shifters, directional compass, antennas, sensors, absorbs, systems for cloning, general cross-section, reduction, etc. by metamaterial systems. The attempts have been made to improve the performance of electromechanical devices by metamaterial systems as well. I'm emphasizing on the performance improved by metamaterial systems. I can mention some Indian researchers, typical, to mention a few. Dr. S.K. Datta of Diageo, MDRDC Bangalore, Dr. Anil a senior class. Dr. A.K. Bandyopadhyay of the same institution. Dr. Sanjay Ghosh's students at CD. Dr. A. Purushottam, now he is with the Professor Pauli at Lancaster University. And of course, very importantly, he is also a student of Dr. Sanjay Ghosh. Dr. Nalini Pari, who did his work in this area under the guidance of Dr. Anila Pera. Sri Kirani Nam, she is at CS in Chandigarh. Dr. P.K. Jain's student, Dr. Manpur Mahato of NIT Patna, and his students. Mr. Amit Kumar Varsne, Professor Prathim Sarkar student at Kalani University, now he is assistant professor in college. Okay. And I hope through deliberations, the participants will know that a helix supported by double negative metamaterial exhibits a negative value of interaction impedance and hence a negative group velocity corresponding to a backward wave power flow, thereby making the structure suitable for a backward wave amplifier or a backward wave oscillator. The double negative metamaterial enhances the magnitude of the interaction impedance, leading to a greater potential for a miniaturization of the structure. The structure can provide multi-band operation without requiring to alter the structure dimensions. For details, you can consult Mr. Rathingo, the research group, Dr. Ghosh, Sanjay Ghosh and Sri Pilani. The speakers in the workshop may like to inform the participant how by metamaterial assistance the transverse dimensions of a folded waveguide fluid structure of a TWT can be increased by epsilon negative metamaterial, thereby allowing for a larger beam diameter and hence a larger beam current, of course a higher RF power of the device. However, now at this stage, I do not like to stand longer between you and the very learned speakers. And giving you a very big thanks to you, thanks to again Professor Sanjay Ghosh. I don't want to stand between you and the non-learned speakers. May I hand over the mic to the host organizers of the program. Namaskar, Jai, Namaskar.
Thank you, sir. Thank you so much. We have our chief guest, Professor Dr. Shubhal Kaur. Dr. Kaur obtained his BSc Physics Honours degree from St. Edmund's College, Shillong, Meghalaya, and BTech, MTech and PhD in Technology degree from Institute of Radio Physics and Electronics IRPE, University of Calcutta, Calcutta University. Dr. Kaur served as professor and head of IRPE-CU and taught microwave engineering and related subjects at IRPE from 1983 to 2016, both at BTech and EdTech level. His field of specialization is microwave engineering, metamaterials, and high energy physics. Dr. Kaur has 3 patents to his credit and published a large number of research papers in peer-reviewed international journals. Dr. Kaur was visiting scientist to Lawrence Berkeley National Laboratory, US, as a Fulbright scholar during 1999 to 2000, when he worked for the development of RF structures for Moon Collider. He was also visiting scientists to various universities and institutes in US, Europe, and Asia, including Oxford University, UK, Cochrane Institute, UK, EPFL, Switzerland, Koichi University, Japan, and so forth. Dr. Kaur was the expert committee member of Summit Kolkata Center from 2006 to 2014 for the setting up of millimeter wave experimental facility and the metamaterial measurement facility at SAMI Kolkata. Dr. Kaur has authored a textbook entitled Microengineering Fundamentals, Design and Application, second edition in 2022, first published by Universities Press in 2016. He has also to his credit another book entitled Physics and Astrophysics, Glimpses of a Progress, published by CRC Press of Taylor and Francis Group in 2022. Recently, another book of Dr. Kaur has been published. The title of the book is Metamaterials and Meta-Surfaces, Basics and Trends. Publisher is Institute of Physics, IOP, UK. Dr. Kaur has also contributed a number of chapters in edited books published by Elsevier, Springer Nature and CRC Press. Dr. Kaur is reviewer of a number of peer-reviewed international journals and the special project proposals of the Department of Science and Technology, Government of India. He is the recipient of Young Scientist Award of URSI and IEEE, MTT and Fulbright Award of the US government. Dr. Kaur is fellow of IET, senior member of IEEE and life member of VETA Society. I think Professor Basu is willing to share something. Sir, please. Professor Basu, please, sir. Dr. E.T. Shah Mishra, ma'am, please. If you share anything, if you want to share anything, please, ma'am.
Hello?
Yes, ma'am.
I could not hear all those things. It was not clearly audible. Do you ask me anything?
Yeah. Do you have anything to share with us, ma'am?
Actually, I already mentioned that for each and every speaker, you have to put a brief introduction as you were doing there. But I do not, every speaker or every inaugural guest may not know each other. So this is mandatory. When Professor B.N. Basu was talking, actually I expected some brief introduction. That is why my thing. And regarding the hybrid mode of operation, next time whenever you do this, you please practice private so that you get you are confident and run it successfully in time. That is my message.
Okay, ma'am. Initially, we have already introduced Professor Basu. So, may I again?
It's okay. Now I understand. Okay.
Okay, thank you.
Go ahead.
Thank you, ma'am. Thank you.
I take excuse from all. I have another activity today in my department after Professor Kaur session. Okay?
Okay, thank you, ma'am.
Hello?
Yes, sir. Yes, sir.
I want to add one thing. Proceedings of this workshop will be written by Dr. Vishal Kesari of DRDO, MTRDC Bangalore, in conjunction, in collaboration with Mr. Raj Singh of Institute for Plasma Research. So that proceedings will be available and it should pass out to IDs. Okay.
Thank you.
Yes, sir. Surely, surely.
Proceedings will be published.
Proceedings will be published and it will be communicated to everyone, sir.
Yes.
Thank you, sir. Yes, sir. Yes, sir. Thank you, sir. Now I would request our chief guest, Professor Dr. Shubal. Yes, sir.
Yes, actually the voice from the center point from where this
not clear. That's what my feeling is.
Okay, sir, but I try our best. It will be clear from right now. Thank you, sir.
Because Usman is speaking, his voice should be clear so that the audience can understand.
Okay, sir. Okay. Thank you. So, request our chief guest, Dr. Subol Kaur, to share his inaugural address and announce the workshop open for all. Sir, please.
Honorable dignitaries on the dais, beloved participants, ladies and gentlemen, I am indeed glad to find that the EC department of Dr. B.C. Roy Engineering College, Durgapur, thinkers in VET Group India and IEEE Kolkata section has organized a 5-day workshop on metamaterial and metamaterial assisted vacuum devices. Metamaterials are man-made, artificially structured materials fabricated with natural materials like copper, silver, gold, etc., but do not depend on the chemistry of the material used for its design. Then what it depends? The properties are rather dependent on the structural configuration of the constitutive properties are rather dependent on the structural configuration of the constitutive artificial electric atom and magnetic atom with which these artificial materials are designed. So these materials are designed with artificial man-to-man interaction is the best thing. Everything else is just of no use. Okay. So it is not dependent on the chemistry of the material, but it depends on how do you place the artificially constructed electric atoms and magnetic atoms. Alright? Any material property is determined in terms of two constitutive parameters, which is the permittivity and permeability. Alright? Electric atom will control the permittivity and magnetic atom will control the permeability. But in this artificially structured material or man-made material, these permittivity and permeability are designer controlled. This is the importance of metamaterials. Right? Why the name metamaterial? Meta in Greek means beyond. Such materials exhibit properties that are not available in natural material. So what is that? The metamaterial is known to exhibit counterintuitive properties like reversal of Snell's law, reverse Doppler effect, reverse Cherenkov effect. Reversal of Snell's law has lot of applications in designer domain to give better antenna design, better micro-passive component design, not only at micro frequency but even at tellers and optical frequencies. Reversal of Doppler effect, people are trying to design new type of radar which can evade the normal radar detection with this metamaterial based radar to be designed to be metamaterial control Doppler effect. And reversal of Cherenkov effect is very important for particle accelerators, because Cherenkovs are radiations and nothing but when a particle moves very close to the velocity of light, it generates an electromagnetic field which is called the Cherenkov radiation. You must have heard that during 2012 when the Higgs boson was detected in Large Hadron Collider, in 2013 there was some problem with the collider because the detector was not able to detect the signal properly. That is because the Cherenkov radiation and the particle moves in the same direction. So particle movement creates some spurious signal that tells upon the sensitivity of the detector. So later on they found that if we stuff the cavities with metamaterial, then the radiation will go in the reverse direction and the particle will move in the opposite direction. All right. So as a result of that, the function of the detector will be much better. So from 2014-15, it has started working, and recently you must be getting some news that this CERN Large Hadron Collider is giving very good results regarding subatomic particles. But that is possible with metamaterial loading in the cavities. Now, who is the pioneer of metamaterial? If that is to be answered, then definitely it is V.G. Vassilagou of Lebedev Physics Institute, USSR in 1967, who first theoretically investigated what happens if permittivity and permeability of the material becomes negative, not positive. All natural materials has positive permittivity and permeability. But he theoretically investigated, if we make both of them negative simultaneously, what is the effect? He found all these counterintuitive effects like Snell's law, reverse Lepron effect, and reverse Cherenkov effect. But there was no solution failure. These things makes really disturbing. I'm sorry to say. So he suggested, rather his theoretical paper suggested that if you make permittivity and permeability simultaneously negative, then these counterintuitive effects are possible. But how to get negative permittivity and negative permeability? It was known to the ionospheric physicists that in ionosphere, below the plasma frequency, permittivity is negative. But that frequency is much higher. In 1996, it was John Benry of Imperial College. He found that if you take very thin wires, array of those, and operate them below their plasma frequency, then you will get negative permittivity at microwave frequency. Fine, you get negative permittivity at microwave frequency. But what about negative permeability? He observed, or we all observe, that when an electron moves, it gives rise to a magnetic field. This is how nature generates its magnetic field, right? So he tried to mimic this in an artificial manner. So what he did, he took a copper ring, make a slit in it, and he called it split ring resonator. So basically it is primarily magnetic, and with a slit there is a capacitance. So this will be a magnetic resonator. So this magnetic resonator will be able to generate magnetic field, artificial magnetic field, without magnetic material. This is the beauty of Henry's work of 1999 to generate artificial magnetism without any magnetic material, right? And in 2001, using Henry's both work of 1996 and 1999 of realizing negative permittivity and negative permeability, the University of California at San Diego in 2001 made the first plasmonic metamaterial in the world. Successful plasmonic metamaterial with negative refractive index. Then the journey started. Right? Now, the question will naturally arise, and Principal Sir will make that question first. What is the use of this artificial magnetism, apart from your so-called counterintuitive metamaterial? Yes, it may be noted that artificial magnetism realized with SLR by Henry has many applications. One application in MRI, magnetic resonance imaging, which we use for brain imaging equipment. If DC magnetic field is replaced by this artificial magnetism, clear soft tissue imaging of brain is possible. And in US, in Japan, in UK, all of them are using this MRI machine and getting very, very clean images of soft tissues of the brain. So there is a direct application of this. Alright? So that the DC magnetic field creates very spurious signal. If you get rid of the spurious signals, then you will have very clear image of brain. Right? Soft tissues. Hence this magnetless magnetic structure will be considered as a new paradigm for manipulation of RF flux in MRI and spectroscopic system. Lot of scopes and applications. Fine. So far, what we can do is the plasmonic metamaterial. In brief, let me tell you. In 2009, we made the first plasmonic metamaterial in India. It was our group at Calcutta University in collaboration with Soviet Calcutta Center and BARC Mumbai. Alright, we made the first Indian metamaterial. If you go to the Google and just type it, India Joints Metamaterial Club, you will find our work reported by Nature India. Alright, so it was in 2009. Anyway, but plasmonic metamaterial, since these are made with resonant structures, alright, so they will be naturally narrow. But if we work with non-resonant structure, then we can get lot done. So in 2002, G.V. L.F. Ferretz et al. Of Toronto University and some other groups like fellows of same university, they used transmission line metamaterial. But transmission line metamaterial is a very simple thing. In my BTech tutorial class, I give a student that you just change L and C of normal transmission line with C and L. Tell me what is the result. Answer is, you have negative phase velocity, you have negative refractive index. So, design of transmission and metamaterial is as easy as that. In the microstrip transmission line, if you periodically load the microstrip transmission line with series capacitance and shunt inductance, you get transmission and metamaterial. And transmission and metamaterial is the basis of design of all broadband metamaterial based antenna, phase shifter, and filter, and so on and so forth. And many of my BTech students have done those designs and have got publications. And on the basis of that, they have got good chances for their doctoral, postdoctoral in places like Harvard, Princeton, Stanford. So these are very, very simple things. We must jump into it for our future career. This is my suggestion to the students. Now, in addition to metamaterial, the new buzzword of these artificial materials is the meta surface. To practically design metamaterial, you should have a 3D metamaterial, 3 dimension. right? And this 3D is not this 3D. It should be periodic 3D. Periodic 3D means to take a checker cube. This is what is a perfectly 3D periodic. Alright? Not this Euclidean 3D, but this periodic 3D. Alright? So, but to design that 3D periodic structure is hell of a problem. And if you want to have the real results of metamaterial, then it should be in the optical range. Because what are the marvels of metamaterials? It can make things invisible with cloaking device. Like Harry Potter cloak. You might question me whether we can make things invisible like Harry Potter cloak. No, not at the moment. But we can make it at the micro level. What is the application of that? Principal sir will be interested in that. When in designing integrated circuits, we need a dielectric lens. And to make the surface of the dielectric lens perfectly plain, we can cloak the irregularities at the micro level with metamaterials, and people are doing that. Alright? Another application of this is people are now really running after and becoming real possible of optical memory, optical computing. In optical memory, there will be the problem of the irregularities, blockage. Again, using metamaterial at micro level or nano level, you can just clean them out and you can have the optical memory possible with metamaterial assistance. So these are all the practical and emerging applications where our boys and girls can work, right? So, and this has to be done with meta surface, not with metamaterial, but with meta surface. What is meta surface? It is a 2D planar metamaterial. But again, here the material term will be again not to be misinterpreted. A surface means it has no depth, right? So all surface properties will come into play. So surface dyadics has to be taken into account, and with the help of that, you have to consider the boundary conditions and not the constitutive properties. This is the beauty of meta surfaces. So lot of people are now working, even in India, on meta surfaces for antenna design and many applications. So I have talked about one of the exotic applications of cloaking. Another exotic application is soft wavelength imaging. So when we do our imaging with an optical microscope, to what extent is our resolving power? It is to the extent of the wavelength. It is limited by that, what is called diffraction limit. We cannot go beyond the minimum resolving power beyond the wavelength. But with meta, why we cannot go beyond the wavelength? Reason is that the propagating the total content of the electromagnetic wave from object to image is carried by two signals. One is the propagating wave, another is the evanescent wave. Evanescent wave dies down just within a quarter wavelength. So it cannot reach the image plane, so we lose the all sub-wavelength finer details. But metamaterial can grow the evanescent wave within the metamaterial, and it can take it from the object plane to the image plane. So in the image plane, you have the sub-wavelength details. So you can have sub-wavelength imaging. And the Berkeley lab, where I worked as Fulbright scholar, their group, Zhang group, is working on this sub-wavelength imaging, and they are demanding that in coming days they can image the individual strands of DNA. And new medical science is coming, where it will be gene-specific medicine, when you have the study of this DNA. So in a decade or so, whole medical scenario will change with this metamaterial solvable way possible in metamaterials, right? But there was too much of exotic matters. Now let us come to our real life matters. Metamaterial inspired antennas, passive components and microfrequency like filters, phase shifters, couplers are found to give better performance aided with size miniaturization. Let me give you two simple examples, which is very common with us. One is called complementary splittering resonator. So in splitting resonator, what you will do, it is nothing hi-fi. You take a FR4 or RT08 as dielectric substrate. FR4 is lower frequencies and RT08 at higher frequencies. You imprint the splittering resonator with metal print, which can be done by simple printed circuit technology. Nothing hi-fi. Then this is how the artificial magnetic atom is realized with splittering resonator. But if you do something that you design the microstrip and scoop out the SRR portion, then it becomes complementary splittering. So if splittering is a magnetic equivalent, then complementary splittering is an electric equivalent, right? So using this complementary splittering structure, you can design patch antenna. My BTech students have done that. And by doing that, they have got a job. There was Skype meeting with them and they were selected. So these are the things which will give us real stepping stone for our future. Another thing is composite right left-handed or CRLH transmission line based filter. Again, it's a very, very simple thing. Take the microstrip line, design it with interdigital capacitor and stub inductance. This capacitance, stub inductance with ground will form its extra capacitance and inductance. Alright? Put them together. So we have composite right left-handed transmission line. With that you design filter. So very, very simple thing, but very, very efficient thing. Result is that your antenna is 24% reduced in size and in performance is much better than normal patch antenna. Filter is more effective, 75% size reduction, and within its very broad band, there is no spurious signals. So very simple things, but very elegant results. So I have seen that they are saying that within 1 or 2 decades, normal microwave, terahertz and digital technologies will be fully replaced by metamaterial based stuff, and they are a US study shows that it will have multi-billion-dollar business in the West. So we must jump into it. These are not hi-fi things, these are simple things. Apart from that, let us again go, not exotic, but something more special. Design of absorbers. At terahertz frequency, material response is very poor at terahertz frequency. But terahertz is now very, very important for concealed weapon detection. Whether this person is carrying a pistol which we cannot detect. With heavy clothing, your metal detector will not be able to do that. More dangerous is whether that person is carrying RDX. Looking at RDX and talcum powder is the same thing. You cannot check him. But allow him to go through this tunnel, and from your terahertz radar, you just shot it. This is called stand-up detection of explosives. So this all can be done with terahertz. How? What is the beauty of terahertz? It has the penetration capability of RF and the spectroscopic capability of optical. And the terahertz is, if you come from RF and if you go up from RF and come down from optical, there is the terahertz. So terahertz considered upon detection and these stand-up detection explosives. Take it from me. DARPA, which is the Defense Funding Organization of US, they are funding 70% of the total research fund for this CWD and stand-up detection explosives. And you must have seen for the last few years, terrorists have been brought into control with all this. So we must jump into this terahertz imaging business. Samir Kolkata Center has already started that, and they take advice from me how to do that. So these things we must jump into. Another is terahertz sensor. For cancer detection, terahertz is again very important because it has spectroscopic capability and penetration capability. For skin cancer and breast cancer, in Japan, in Australia, in US and UK, they are using E-ray imagers for cancer diagnosis, very early cancer diagnosis. And for this T-ray imaging, as terahertz has more material sensing capability, when you add metamaterial to it, its sensing capability increases enormously. So terahertz assisted sensor design, which is very simple. You just again you use those split ring structures and all this. Everything is given in my book that is published. Everything is given in that book. So you can have these terahertz sensors. So in medical diagnosis, in coming days, this whole scenario will change with these terahertz sensors. But that should be metamaterial assisted. Or in today's term, meta surface assisted. Now I come to the topic of today, that is vacuum tube designers. There is a beauty in metamaterial or meta surfaces. Professor Basu was mentioning that it is called backward material. That means in normal light-handed material, natural material, the propagation vector goes in plus z direction. But in metamaterial, it goes in the minus z direction. That means the propagation vector in the minus z direction, so it is called backward. Alright? So, for antenna designer, this is a beauty. In antenna design, you can tilt your antenna with phase antenna in one quadrant only. But if you use metamaterial, you can do it in two quadrants. This is the beauty. And this vacuum tube people are also using that. Because in tube design, you need to control the phase. If you have the facility of controlling the positive and negative phase, you have the marble in your hand. Alright? This is the beauty of metamaterial meta surface. It's different inclusion structures, but what this vacuum tube will utilize. Okay, finally I conclude with my. I find that the program chart of this workshop is loaded with very, very important deliberations in metamaterials and meta surfaces covering a wide range of developments in this field, including metamaterial assisted tube developments. Eminent speakers will help the participants to understand the intricacies and the scope of future development possibilities in this emerging field of research that demands knowledge in electromagnetics covering microwave through terahertz to optical frequencies. This last sentence is very important. It demands the knowledge in electromagnetics covering microwave through terahertz to optical frequencies. I also find that some software demonstration will be made on the last day of the workshop, and I hope this will benefit the participants as simulation-based design of metamaterial and meta surfaces are important before one goes for fabrication of such structures. I was talking with your principal today that look, we need simulation. Without simulation, we cannot design our structures these days. Fine, but we should not be lost in the labyrinth of simulation. All right, we must have fundamentals clear. We must have our goal clear for our design. Only then the simulation can be translated to real stated design and final useful product. So that should be kept in mind. I am sure the young minds will learn a lot from the expert lectures to be delivered in this workshop by many speakers during these 5 days, and the participants will have a lot of food for thought to take thought as take-home reward. Our main reward is what we take back home in our knowledge bag. Before I conclude, let me, at the end of the lecture, let me introduce myself. If you allow me to introduce myself, then the only introduction is that I am a learner all along my life. There is no other introduction. With these few words, let me express my best wishes to all of you and great success. Thank you.
Thank you, sir. Sir, please announce this workshop as open for all.
Yes. It is my pleasure to announce that the workshop is open for all, and let it be a grand success, and let it translate to the usefulness of the participants. Thank you.
Thank you, sir. Now most of the deliberations are online, so you may please avail them on seats.
Thank you.
Now we are having our another guest lecturer, Professor Claudio Paoloni. Professor Paoloni is a professor of electronics and Cockroft Chair at the School of Engineering at Lancaster University. He has been the head of engineering department and first head of School of Engineering in the period July 2015 to July 2022. He is senior fellow of the Higher Education Academy in the UK. He is distinguished lecturer and was member at large of the Board of Governors of the IEEE Electron Device Society. He is associate editor of the IEEE Transaction on Micro Theory and Technology. He is author of more than 260 articles in international journals and conference proceedings in the field of high-frequency electronics. He holds 3 patents. He is lead guest editor of the special issue From Mega to Nano, Beyond 1 Century of Vacuum Electronics of IEEE Transaction on Electron Devices, June 2030. He has been coordinator of the Horizon 2020 project. Through the traveling wave tube-based W-band wireless networks with high data rate distribution, spectrum, and energy efficiency, and of the Horizon 2020 ultra wave, ultra capacity wireless layer beyond 100 GHz based on millimeter wave traveling wave tubes. He was chair of the IEEE Electron Device Society Vacuum Electronics Technical Committee. He is IEEE senior member. He served in the organization of many conferences and workshops. I would request Professor Paoloni to continue with his deliberations. The chairperson of this session is Professor Dr. S.K. Kar. Thank you, sir. Professor Paoloni, you may continue, sir.
take the I don't have one second. Let's see if I can have some setting. I see where I can share the screen because it seems like tools.
একবার বেরিয়ে শেয়ার করেছিলেন একবার
Okay, then I get it. Mr. Baldani, can you enjoy the tools? Go ahead and enjoy. The drawing? Yeah, I think so. Okay, because now it is visible. Okay, let's see if let's see how I can show you the. Let me check. Do you see now? Yes, sir. Now it's visible. Okay, that's all. Okay, let's go. Visible? It is. Can you unpin Dr. Sarenko's screen? If you unpin Dr. Sarenko's screen, you can see. Now yes, okay. Can I go on? I cannot see. Okay. Let's start. So do you see the front page of the
এই সেশনটা শেষ হয়ে যাচ্ছে না সেশনটা শেষ হয়ে যায়
Sorry, because I don't see here. Yeah, you see it. I think you see it.
তিনটে নাগাদ দেখো তিনটে
Okay, I can start the presentation. Thank you very much. Thank you very much again for the invitation. I will give a general talk on the importance that we improve because I see that in the program there will be a number of experts that discuss much more detail on the metamaterial system electronic device, but the application of the metamaterial. Group my please. Sorry? Other participants to group their mic please. Sir, do you see me? I don't know what Yeah, you are visible and your screen is also visible. Absolutely no problem. So I can continue. Yeah. Thank you. I understand that you see where I am now. I'm after of UK is the Lancaster University of unfortunately, I would be very happy to be there in person. So straightforward. Then this is my lecture about Dr. Stephen, Dr. Moy Joshi, and also I give with my memory, my collaborator, Graham, and now that unfortunately not very good as I go from the activity of my group. Let's start with the definition of what is terms radiation. Terms that are quite used in different ways depending on what we can say. However, in reality, we can say
non-destructive inspection, and the resolution of software is not high and light, but is much better than microwave. So there are advantages for this point of view. Then can be used for imaging. You can see that actually, depending on the diffraction limit, the value of the resolution, you can see from the image here that you can see the contour of an object with this resolution. The frequency of adherence, the object is very, very clear. The interesting thing is that you can inspect the circuit without opening. This is important for testing and after production of the circuit. Another thing, for example, we use passing the layer of different artwork and see in the pattern, for example, in paintings. And so this is extremely important application. And then actually this was an old quite important application that we from the simulated interest. The radiation is executing imaging due to the fact that the Per's radiation can pass, can penetrate typical material that are made clothes and bags. This permits to have a quite good possibility to detect element. At the moment, you know that the probably high frequency device that is used is the Dodge class gate that I think that is working microwave or in a wave, and after some ways replacing on system lower frequency. But however, obviously the concern in this case are related to privacy, to other aspects that the can contain by Per's frequency permits probably to very attention, and also permits to reduce the error that the low resolution system would provoke because the images would be not so well defined. Then, so that fusion, you know that it's extremely on the topic of the video and not on activities. Also, I know that there are important work on production of journals for 200 years for producing the streamline outlet for the ignition of static fusion. But fusion is not only streamline outlet, but also is the problem that the turbulence of the plasma that is streamline temperature could have possible impact on the walls of the reactor, and not liquid temperature at the level of 100 million degrees, no material stable resistance, so the confinement of the plasma should be extremely accurate. For the reason, the radiation important for studying the plasma turbulence. We can see an example section of the plasma toroidal shape. And the interesting thing is that the electron cycle radiation of in case of the plasma in the nuclear reactor range between 15 years after that. So substantially is in the sub-Per's radiation, and then this helps to create a detector system like scattering to study the plasma and then find solution to make it more comparing to the previous application, this is extremely broad market that is actually present in all the countries, usually Western, everyone uses mobile phone. But also there are a number of new applications that are IT and autonomous vehicles, remote surgery, and that now also there are the new frontiers of the AI that is not still clear how will be embedded in the communication system. Also, in this case, the surveillance spectrum is extremely important because at the moment most of the communication, the wireless communication are obviously at level of mobile phone below 6 gigahertz, mostly 2 or 3 gigahertz, some tend to go higher. There are leads at 24 gigahertz, depending on that is exploited. For wireless link point-to-point transport data, there are now well established band technology, band between 71 and 86 gigahertz, around 8 gigahertz, but at the moment it's limited to point-to-point link and links and the low power of amplifiers at this frequency requires very large antennas, so the width is high, and probably you know that the cost of a link is not only the device but also the renting of space of a building when full. However, there are three wide bands, the W band, the band, the G band, that offer more than 100 gigahertz available for transmission, and these now are heavily restricted to use for wireless communication. So, but also they are charged one because the technology and increase of the frequency is more expensive because you need very efficient materials and skilled operator. So there is the limit in the technology because still there are our amplified solicitation and low power, and then in the sense not working at this frequency, especially in band, there are constraints to the technologies. However, it's true that it's possible to have bands hundreds of gigabits per second, and if we consider the full bandwidth we can achieve, use the 1024 form modulation around 1 terabit per second. Obviously, it is not possible to cover the full bandwidth, but even the sense that the solutions of that spectrum would be extremely beneficial. The problem is that the path loss is extremely high. You can see that at 2 gigahertz, the displaced path loss is 70. If we go to 100 gigahertz, the number doubles. This is a substantial challenge. Unless the distance is very short, but for a substantial distance, this poses challenges to the application through the technology. And also, in addition to the displaced path loss, we have valid here, because in the first design build, it was invented by Fleming sort of about in 1845, probably that would be other attribution, but it's one of the most reliable. And in 1942, Conrad invented the WT and built the first industrial WT. You can see this probably was a pretty challenging form at that time, but now it opens the electronic bank. For many years, the DWT was the only power amplifier available. The DWT works on it's a simple method in the sense that we have an engine that powers the guide structure with given electron speed that depends on the voltage applied to the electron to the emitter of the electron, the anode, and the current, and the accelerating anode. The waveguide that could be not the normal waveguide, but usually called the structure, has the purpose to reduce the speed of the phase velocity of the wave, this typical range of the speed of light, to the practically phase velocity equivalent to the velocity of the electrons that covers the guide. So this permits that for each electron that enters the waveguide to be associated with a certain phase of the wave propagating and maintaining the position so to be exposed then depending on the entrance of the electron in corresponding to the wave to be exposed to an uncertainty of the accelerating field. This determines that the electron accelerating field are accelerated and the electron in the accelerated field are accelerated and the electron in the radiated node are not the same Materials speed. But then after a while, after the faster electron reaches the slowest electron, and then it starts to form aggregation of charges that result of the darting cross of the wave, and due to the fact that the aggregation of charges are very high density in terms of mass, because they are made by metal electrons, when reducted, the energy you lost the slower reduction of the speed is conserved and transferred to the radio frequency field and with the amplification. Here there is the mechanism that you can see of the waveguide that the field that accelerated the electrons, and then after a certain distance, you can see the formation of these bunches that then they are reducted and transferred. The lost kinetic energy is transferred to the electromagnetic field. The important process is that having after the vacuum, so there are no collision, and this makes it possible to have a level of power that solid state amplifier cannot have, because solid state electrons travel in a regular with continuous collision, production of very high thermal effect in the region of interaction. Instead, in the traveling tube, the thermal effects are reality completely concentrated in the collector, and that in carrying these electrons. Then there is another that accelerates the electrons. The electron beam travels along the flow structure that we can see many different ways to certain frequency. Then there will be an input and output port. The input port, these are called windows where there is a sheet of dielectric material that has the purpose to be transparent to the wave and seal the tube in order to maintain a level of light of 10, 99 or 10 over. And then there is a repository where the beam after travel is recovered, and usually the electron is kept at lower voltage in order to have direction and in some way reduce the speed of electron, they will not collide with the walls of the electrons, but are absorbed and then the current is recovered. And this also permits to have efficiency that is possible for solid state device. So these are a number of advantages. The main parameters are for the design and the dispersion. The dispersion substantially is the capacity of the waveguide, high waveguide for the structure, to ensure for the required bandwidth that the phase velocity is substantially constant, because obviously the electron velocity is set by the voltage of the beam and is constant at single value. So in order to have the interaction of a large frequency band, all of the frequency in the band should have the same phase velocity, similar to the phase velocity of the. And this is one design parameter. The other design parameter is the interaction impedance, that is the measure of the capacity of the lowest fraction to extract energy from the electron beam. The higher the interaction impedance, the more effective is this process. And this depends on the electric field variability and the pointing vector inside the waveguide. And then the beam voltage and current that are like parameter and determines different aspects. One is the shape of the structure, the other is the magnetic field, the other is the power supply, because the power supply probably is the most bulky part of the DWT, even is external to the DWT, but also it is important element to determine the use of the DWT and the market value. So looking at the famous images, we can see that there is gap between 0.1 and 1 terz are the number of devices, but the devices that are more powerful are either extended interaction time or a narrow band or a split band, so not for use for conversion purposes of all devices. So let's look at the subterranean tubes. In the subterranean tubes are providing extremely precise application and precise alignment. We need reliable manufacturing in a electron structure. The surface should have extremely high finishing because the decrease of the frequency, the skin depth decreases a level of, for example, 1 gigas or terabits in nanometer, and it's really a of application possibility. Then the material should be compatible with the strict vacuum with the different products, not all the material can use copper is extremely good for the purpose, but not easy to manufacture. And then the alignment of different parts, because not they are working with extremely high radio beam that are very, very small diameter, but for a very long length. So fabrication is something that can be done, but often requires substantial skill. The gaps are another important aspect, especially for that we choose. Would be great to have a carbon with high carbon density, to have a long lifetime, in order to create small cross section and continue with a high current, and remain also a sort of the contacts, because they are very small, very robust and not need of high temperature. The vacuum is required for all the tubes, not difference here, but this determines further complexity, especially for the windows. Then the interaction structure, because the tender units are microwave extremely effective because it works in the fundamental harmonic and extremely high interaction impedance. This is not possible to build the newer structure there, and so the novel circuits are necessary enabling the interaction of these fields. Then low cost already said, because at the moment are still is, in my view, much easier to build because it doesn't need any alignment comparison for the guide. Obviously, the counting is a bit more complex because it's not the guide. Also, in this case, the immediate expansion of the velocity and adverse function of the frequency. The double stack grading, this is from University of California. This is built to support instead should be required plastic structure that was built, I think, up to 260 years. And the structure is very that were changed differently from the pencil tip. It is permit a lower current density for the same current due to the fact that the span of one section. And then there are examples of metal lines. Metal lines, in principle, are much easier to build because are built from simple lithographic process. We can see here, for example, extremely important experiment demonstration of how to build the sort of iris by very sophisticated fabrication process that you band. And an example at lower frequency and band. In principle, the structure is more effective in the sheet beam, but can be used also for a cylindrical beam. However, all the structures after are called to replace some way iris, but it's still not, but no one of them has the same performance, so some compromises are needed. Now let's see the application. You can see here, for example, a typical 346 gigahertz of 0.346 terats example of double propagated waveguide built for plasma diagnostic. This is built by sensitivity, and this size is 60 micron by 60 micron for the height of around 120 micron. And you can see that this is required extremely sophisticated fabrication process, but this physical obviously this can be done also by lithography, by ellipse, by sensitivity is possible. This is then an example of the fabrication of all the waveguides or built in the framework of a figure. And you can see that this is only one half of the waveguide, the other half is exactly the same, and the two parts should be perfectly aligned on follow the edges of the waveguide. Obviously, this requires extreme accuracy, otherwise all the waveguides were not aligned would bring the stop band and other processes. This you can see the fabrication. Then another process, this for extremely high frequencies, for example, the deep X-ray lithography. This was the example of 1 tera's backward wave cascade amplifier, and the pillars here are 20 microns by 20 microns by 60 microns with a beam of around 20 microns diameter. This is extremely high technology that not very specific for hand activity, for instead much more affordable and cheaper, only 100% process provide the liga and filiga that is also a lithography process that permit to build the bill, in this case 70 microns, 30 microns, 50 microns, with lithography, with electroforming, and it is much more affordable and used quite commonly for some tenants DWTs. The state of the art, just to give you an idea, this is for example a band 1995 years DWT that's made for the guy. Just to show you the challenge for the guy, you can see that if not properly challenging. This, for example, is 140 years for the weekend built by USSD China, and you can see that the performance are around 1.5 watts, so quite good as first test, demonstrating that the tube is feasible. If we go higher frequency, this is an example of built by the DARPA project for 120 gigas DWT based on double stagger low extraction, and you can see that the gain is quite high, the power extremely high, reaches a certain point around 100 watt. Probably these are required extremely sophisticated technology, not very suitable for low mass production, but this is a demonstration of how even under subtherapy can be extremely high power. And then is an extreme example of application of 1 terabyte amplifier for the waveguide that was extremely sophisticated is by Northrop Grumman, assuming that it is a 55 waveguide. So the absolutely fantastic work. Then now let's go to the I want to the project, the portion D. One of the problems that we had, for example, is the use of in this case, the simple torpedo waveguide that, as you can see, the field distribution that is quite broad over the top of the propagations, and permits it so to use very wide sheet. And the problem is that we found then that having again improves the performance, creating this long feeds propagation. But the problem is that how to make the navigation better frequency. We are talking 650 gigahertz, 0.65 hertz, where the dimension you can see are the width of the waveguide is only 20 microns, so it's very tiny. And to make the navigation realistic and to make the assembly. So we introduce the concept of photonic crystal. Crystal arrangement periodic molecules. What is discovered that the electrons in crystal propagates as a wave, and it's possible by probably modifying the crystal, depending on the crystal, to have a certain way permitted and so creating gaps in it. The photonic crystals substantially are the result of equivalent periodic structure where instead when atoms and molecules we have a specific structure that determines with different direct constant the properties of the typical of crystal. So in practice the photonic crystal would be designed in order to have the so-called photonic backend where a certain range of frequency is considered to propagate. In this way, we can create substantially a metal wall more shaped for a given frequency range. It is very similar to a metamaterial, but the use is different. The material is a sort of full material where we propagate. Instead, here is the sort of use of periodic structure to confine the wave or to block the propagation of the wave. Then, this is what we see. This is a typical waveguide where instead when the metal walls, we create the sort of virtual metal wall that are specific to crystal, and then its behavior as they were metallic walls. This advantage is that it's much easier confinement, and the frequency outside this range would be absorbed and not disturb the interaction inside the waveguide. Then this is the comparison between conventional waveguide and blood crystal waveguide for the PWO. You can see that the electrical behavior is practically exactly the same. The field, the propagation is exactly the same. That demonstrates that the behavior is determined by the presence of the photonic band gap. Also, the number of rows can be changed depending on the level of the gap needed that would be less, giving the structure more compact. The counter is another important development of this problem, because typical counters are mandatory dependent with guidance with the sun that matching, and the wave should in some way move from the channel to the input output port. Instead, using the photonic crystal and with some effects, it's possible to bend without practically no losses. And this is a big example of a counter where you can see that the wave follows the path between the photonic crystal system, and there is no practical losses. You can see here counter and counter at 90 degrees. You can see that the performance are much better over wire, very wide bandwidth, and there is substantially extremely good alignment, because the wave is forced to travel in the band gap, and so there is no loss, no reflection, no other issue with the metal down. And this is what the first test that we did at that time in very low frequency, but to demonstrate the principle of the photonic crystal. Now then, at Lancaster we have something that we had that is a sort of the lab, and so we have all the material built internally by waves, potentially around 140, possibly even higher, around 250 gigahertz. This is to introduce what is our work. Our work is to find, design, and produce primary tubes for wireless link at frequency, in this case, without 1D band, without G-band. This project is a project almost finished. It's to produce a G-band 1 link with 40 gigabit per second for 1 kilometer distance with 99 availability. Use of K. Use of K means that the availability at 99.99 is happened when the rate is at 42 meters per hour. That's quite relatively heavy rate. And the purpose to do this, obviously, not only data defined component available, and that is 10 watt concentrated power for the antenna gain around 50 gigahertz. Per meter is frequency to be very compact, about around 10 centimeters or less. The system is based on transmitter receiver over two different bands of the band, so we use the 10 gigahertz and 151.5 gigahertz, 164, and another 10 gigahertz aggregation between around 151 to 170 for here there is a region where the mission is forbidden. And the way it works is frequency loop, so there is simple, and then it's going to exploit the bandwidth as 64 that provide 45 gigabit per second in real condition because there is applied forward correction error or 1.75, so very conservative. And in a very high range system. These are an example, at the moment we are designing a single stage identification of because to very challenging application at the end. This is virtual line, you can see that the double creative guide has been designed over this one band that cover between around 129 to 150. This is the interaction impedance that is clearly very low at this frequency, and it's not the problem of the extreme frequency is there, it's a range where increase of the peak of interaction depends to degrees, but however, with increasing the number of meters, it's possible to achieve the power needed. Then the next parameter over the full bandwidth are quite good. This is for limitation of the counter and the lower structure. And this is the gain for a single stage, but then often expected for the stage amplifier. You can see that again at the moment is built as a lower frequency for also another project. It's around 20 dB and with more than 1.5 watts. Adding 20 gain more or less, hopefully you can reach adding more than 15 gain in comparison to 10 gigahertz 10 watt needed. These are was built into blocks that show how the construction is will result after application. This is extremely challenging because of the working copper with very high tolerances. And this is an example how the fabricated blocks are. You can see the put the output here. There is the electron beam electron beam candle that for the electromagnetic collector there are alignments, and the quality is extremely high because the pillar are 149 sections, so extremely small. This is also still a challenge, the fabrication and the cost of fabrication. The feasibility is demonstrated only to have a device that is suitable for large production. The fabrication should be simplified. And it is out that with the assembled at the level of product, obviously not optimized, but working. Then, future perspective, in the way that the analysis can be done, also is able to be a substantial challenge for solid state, especially for layers, because solid state at the moment, no matter the technology, cannot analyze it, are still far to have performance comparable to the IoT, and the high equation, the signal loss are poses a huge obstacle to the propagation. Also, there is a much more work. I acknowledge that extremely very active work of we had the group of interesting electronics that with a lot of ideas, so I'm very grateful of the work. Then I would like to announce that the special issue that I led as chief has been released 2 days ago. Here you can find fantastic number of papers, also 5 cited papers that covers major aspects of electronics. One is on applications, 2 are modeling, 1 is the field of application, another one in the field of multi-beam lines. So if you even if probably most of the people were already released down the full issue of the release, and then hopefully you enjoy. And then I would like to conclude with something that you know very well, is now in live Banco Electronics website, is the fantastic achievement of Professor Pan, that I don't know if you know, I have the outstanding honor to be the nominator, and I'm very proud that very privileged to be the one that has put forward the excellent career, unique career of Professor Basu for his John Pierce Award that for probably the first time we are recipient, and make us very proud to be part of this community, and we are very grateful to Professor Basu for his continuous and restful support of the Banco Electronics with the idea, with the engagement, example, is really a career that all of us hope to achieve. And so thank you very much indeed, only to see that also we are part of the UK, and thank you again for the opportunity to be part of this fantastic community.
Thank you so much, sir, to share your pragmatic experiences with us and to allow us to give some time to spare with us. Thank you so much. We hope we'll have your association in future again and again. Thank you so much, sir. Thank you, sir. Professor Fuka, we request you to share something with us. Sir, please.
It was a pleasure listening to Professor Basu again, and the vast amount of area that he covered, starting from metamaterials, how they are going to be useful, and then the details on elements used in temporary tubes, and an enormous amount of compilation and very wonderful presentations with very rich ideas that can be harnessed for the telecom business, that can be harnessed for improving the quality of transmission. And for majority of the cases where we are starting to have slightly higher power, so that things can be more powerful, things can provide better bandwidth and better data rates. And thank you, Professor Gowdy, for your wonderful talk. And I'm sure we are all proud of Professor Basu for the Pair Award. And I'm also sure that Professor Gowdy will be associated with various other institutions in India to collaborate and to have some hand-holding for further expansion of work in the area of metamaterials and the associated vacuum tube devices. Thank you, Professor Gowdy. Thank you to the DC Royal Engineering College. Thanks to Professor Basu, and thanks to Professor Khan for inviting me to be part of this. Thank you all.
Thank you very much.
Thank you so much, sir. Professor Lolit Kumar, do you have anything to share with us, sir? Professor? Sir, you are not audible, please.
It's always a pleasure to listen to Claudio, for the always bring something new, as what we are getting now, and in a university environment, we set up ethical treatment. There are people living in the highest or the world highest student. And we in India are able to listen to him and get benefit of what he. So thank you very much, and thank you.
you have any query? Anything? Thank you, sir. Thank you. Sir.
I think it was a very lucid lecture, and most of the people are still thinking about what all he talked about. So maybe he will have some questions later on.
Okay, thank you, sir.
Thank you.
So, I need your permission to conclude this session right now.
Yeah, please conclude the session and thank you all. I also take your leave because it's too late now here.
Okay, sir. Our next session will start from 3 p.m. onwards. Thank you, everybody. Thank you, sir.
Bye.
Thank you, sir. Bye.
ক্লোজ করে এক্সিট
Yes, sir. Next session will start from 3 p.m.
That